Okay, so this is what happens with f. What about, okay, so we can go on from here, right? We can go on to all the other tensors, but in particular, let's be focused here and look at the tensor that's relevant to studying fluids. We've got the tensor F, we know how it transforms, and this is the tensor that's relevant to studying elastic solids, right? Especially hyperelastic solids. So now let's look at the tensor that's relevant to studying non-ideal fluids, okay? And that tensor, if you would recall, is the spatial velocity gradient tensor, right? Because we said that a non-ideal fluid is a viscous one, spatial velocity gradient, and for viscous fluids, the viscous stress depends upon the spatial velocity gradient. So now let's look at how this quantity transforms, just to prepare ourselves to go ahead and study the constitutive relations. Okay. So the spatial velocity gradient is this, that's its definition. And when we derived this a while ago, we demonstrated that it is equal to F dot F inverse. Okay? Now, so what we see is that under the rigid motion, under rigid motion of omega t to omega t plus, and we know how we're going to write that rigid motion. We've done it on the previous slide. We will have this, right? Okay. All right. Which is, okay. Observe that I've got a transformation on the operator also. And this is because we are talking not only of how the vector transforms, v, but the space with respect to which we are computing this gradient is itself changing under the rigid motion. Okay? That's why we have the plus on the x as well. Okay. Now, conveniently, we have this, this relation. And just before this, we've looked at how f transforms. Okay? So this is essentially now partial with respect to time of f plus, okay, all of this f plus inverse. Okay, we have this relation for f plus where the q is a function of time. Okay, so now we can calculate all of this. Okay. For the first term in parentheses, we get the following. We get q dot f plus q f dot, okay? And this is because, remember that this object is q f, right? Time derivative of that object, right? That's what that partial time derivative is, right? Because that's how f transforms to f plus. Okay, so the first parentheses is what I've written out here, and for the second parentheses, it's just the inverse of qf, right? Remember, the inverse of a product is the product of the inverses with the order flipped, right? So we get here f inverse q inverse, but what is q inverse? Q inverse is q inverse, because q is orthogonal, is q transpose. Put it all together and we see that for the first term we have q dot f f inverse, q dot f f inverse, I'm going to write this as q transpose, plus q f dot f inverse q transpose. Okay? Now, here we have the isotropic tensor. Okay? So when we put things together, what we see is that the transformation of the spatial velocity gradient tensor goes as q dot Q transpose plus Q F dot F inverse Q transpose. And this is our original spatial velocity gradient tensor. So, our spatial velocity gradient tensor also does not transform by the rules of objectivity. Okay? Because it would be fine if it were just the second term, but we have the first term in there as well. Okay? So, it is not objective. All right? However, there is hope. Okay? Let's look at what happens with the symmetric component here. Okay? But that symmetric component is what we denoted as D plus, okay? As D originally, so we're going to call it D plus now. It's the symmetric part of this. Okay, and all of this came from our definition of D being the rate of deformation tensor, which is the symmetric part of the spatial velocity gradient tensor. Okay? So if we compute the symmetric part of the transformed spatial velocity gradient tensor, here's what we get. Okay? We need to have the symmetric part of Q dot Q transpose plus the symmetric part of Q F dot, well, I don't need to write that as F dot F inverse. I'm going to write that as Q spatial velocity gradient Q transpose, recognizing that I have this relation here, right? Okay? Now, do you remember something about Q dot Q transpose? We demonstrated a while back when we studied rigid motions that Q dot Q transpose is skew symmetric. Okay? Okay? Therefore, the symmetric part of Q dot Q transpose is 0. Okay? So, we need to only worry about the symmetric part of the second term. The symmetric part of the second term is 1/2 the term originally plus its transpose. But what is the transpose of that object? It is Q transpose, the whole transpose, gradient of V transpose Q transpose, right? The transpose of a product is the product of the transposes, but with the orders flipped. Okay? Okay, so what we have here then is 1/2 Q spatial velocity gradient Q transpose plus Q transpose, the whole transpose is Q, spatial velocity gradient transpose, and Q transpose is, well, Q transpose. Okay? It's the final step. I'm going to write that out as, this is what we started with, 1/2. We basically get Q spatial velocity gradient plus spatial velocity gradient transpose Q transpose. Okay? And when we realize that we can, of course, we can move the half inside, right? And what we see is that this is actually q times the symmetric part of the spatial velocity gradient, which is d q transpose. Okay? So, whereas the spatial velocity gradient itself does not transform objectively, the rate of deformation tensor does transform objective. Okay? So what this says is the rate of deformation tensor is objective. Okay? So we're going to stop here, but the good news is that we're completely equipped now to come back in the next segment and go through these rather tricky arguments of objectivity of the relevant constitutive relations for hyperelasticity and viscous fluids. Okay? We'll stop here.